the next question is also on the topic of linear independence, a topic which we looked at in the last video. So the next question that we have, exercise 1.1.5, this says show that the following row vectors are linearly dependent. So we want to show that these vectors that I am writing right now we need to show that these three vectors are linearly dependent, and then we need to show the opposite for we need to show that the first set of three vectors, these three vectors, are linearly dependent. Then the next set of three vectors are linearly independent. The opposite meaning linearly independent. So the topic of linear dependence and independence we had looked at in the last video. We will just recap it a little bit over here. So for linear independence, we had the following condition. The condition was that if we take the superposition of the given vectors and set it equal to the null vector, then the solution for this is that all of these coefficients ai in the superposition are 0. So if this relation is satisfied with all ai equal to 0, that is only the trivial solution, then we have linear independence for the given set of vectors. And linear dependence would mean that if we take this superposition of all the vectors and set it equal to the null vector, that means we get some non-trivial by non-trivial meaning non-zero values for ai. This can also be rewritten in the following manner, that we can write a given vector out of the set of linearly dependent vectors as a superposition of all the other vectors in that given set. So this is just a recap of linear independence and linear dependence which we saw in the last video. So let us now try and solve this question. So we need to consider the linear superposition. So let us take that. Let us take A1 for the first part, in which we need to show linear dependence. So let us take a1 times the first vector plus a2 times the second vector plus a3 times the third vector, and then we set it equal to the null vector. So the null vector in this case is nothing but the triplet of all zeros. Now let us try and solve this. Before that, we need to see the system of equations being formed by the above equation. So the system of equations is a1, let us use the property of scalar multiplication for these vectors. Then we get this. So this is from the definition of scalar multiplication. This thing over here was our null vector, and then let us add these. Then what do we get? a1 plus a2 plus 3a3 comma a1 plus 2a3 comma a2 plus a3. This is from the definition of addition. So finally we get the system of equations as a1 plus a2 plus 3a3 equal to 0, a1 plus 2a3 equal to 0, a2 plus a3 equal to 0. So from the above equation we get this system of linear equations in 3 variables. How do we solve them? We will use the matrix method. So what is this? This is system of 3 linear equations in 3 variables, and we will solve them using the matrix method. So let us form the matrix of the coefficients of these variables. So the matrix of the coefficients corresponding to a1, a2, a3 would be 1, 1, 3, 1, 0, 2, 0, 1, 1. This times the matrix of the variable, sorry, the column vector of the variables will give us the column 0. Now we will solve this using row reduction. So the first row operation, first we will write it in the augmented matrix format, in which we will not write this variable column vector. So the augmented matrix format for this would be just writing down the coefficients and the 0 column matrix. So this is the augmented matrix format, in which we do not write the variable column vector. We just write the coefficient matrix and the right hand side, that is the constant column vector, which is in this case the null column vector, and then we will apply row reduction to this system and subsequently find out the values for a1, a2 and a3. So the first row operation that we will apply is row 2 goes to row 2 minus row 1. What is this going to give us? So row 1 is as it is, row 2 is row 2 minus row 1, so this, and row 3 is intact as it is. So we have managed to make this element 0. Next we will move to this element over here. We want to make this element 0. So the row operation corresponding to that would be row 1 goes to row 1 plus row 2. So 1, 0, 2. So we have made this element also 0. Then this is a pivot element over here. It's the first non-zero element in this row. So this we want to make positive 1. So this we will go right. Row 2 goes to minus row 2. So after row reduction we get this. So this is nothing but the reduced row echelon form. So in reduced row echelon form, each of the pivot elements is 1 and entries below the pivot elements and above the pivot elements are 0. So we have this as the first pivot element, all elements below that is 0. This is the second pivot element, the element above and below that is 0 again. So this is the reduced row echelon form. So clearly from this reduced row echelon form, we will be able to find out the values for A1, A2 and A3. So corresponding to this, if we write down the set of equations, that would be A1 plus 2 times A3 equal to 0 and A2 plus A3 is equal to 0. So this means A1 equals to minus 2A3 and A2 equals to minus A3. So this is what we get. Clearly what we have is A1, A2, A3 is not equal to 0, and for one particular solution, so a particular solution would be if we set, let's say, A3 equal to 1, then we will get A1 equals to minus 2 and A2 equals to minus 1. So we do have a particular non-trivial solution for the given system. So this means that we have shown that our given set of vectors are linearly dependent because we have shown that the values for A1, A2, A3 are non-trivial. So this particular solution meaning non-trivial solution. So non-trivial means that it is not linearly independent. That means it is linearly dependent. So from the solution what we can write is that minus 2 times the first vector. The first vector that we had is 1, 1, 0 minus 1 times the second vector 1, 0, 1 plus 1 times the third vector is equal to the null vector. This can be rearranged and written as follows. What we have is that the third vector 3, 2, 1 can be written as a linear combination of the other two vectors that we have, of the first vector and of the second vector. So because such a relation exists, that also shows that these three vectors are linearly dependent. So we have shown the first part of this question of showing that these three vectors are linearly dependent. Now let us move to the second part of the question that we have. So in the second part, we have a different set of three vectors and we need to show that they are linearly independent. So again, let us take the linear combination. So a1 times the first vector plus a2 times the second vector plus a3 times the third vector, and then let us set it equal to the null vector. So again, let us use scalar multiplication. So this is null vector, this is scalar multiplication, and then let us add them up. This is from addition. Again, we will write this equation in the matrix format. So in the matrix form, the coefficient matrix would be 1 1 0, 1 0 1 and 0 1 1. Variable column is again a1 a2 a3. This is equal to the null column. So again, in the augmented matrix format, we will not write the variable column, we will just write the coefficient and the null. Again, we will use row reduction operations. So the first target is this element, we want to make this 0. So we will use the operation row 2 goes to row 2 minus row 1. So we have made this element 0. Next, we want to make this element plus 1. So you will say row 2 goes to minus 1 times row 2 . Then we want to make this element 0. So that would be row 1 goes to row 1 minus row 2. Then we want to make this element also 0. So that is row 3 goes to row 3 minus row 2. Now we want to make this element 1. This is the pivot element. So row 3 goes to 1 by 2 row 3. And then now we want to make these two elements 0. So row 1 goes to row 1 plus row 3. Sorry, row 1 minus row 3 we want. And finally, we want row 2 goes to row 2 plus row 3. So this in our case right now is the reduced row echelon form. And from this we can see what we get as the solution from this reduced row echelon form. We will get A1 equal to 0, A2 equal to 0 and A3 equal to 0. So that is, this is the trivial solution. So from the definition of linear independence, if we take the linear combination of the given vectors and set it equal to the null vector, and if the coefficients, each of the coefficients of those vectors taken in the superposition come out to be 0, that is if we obtain the trivial solution for the coefficients in the superposition, then what we have is a set of linearly independent vectors. Linearly independent. So we have completed this question. We had to show that the first set of vectors is linearly dependent and the next set of vectors are linearly independent. So these were two videos on linear independence and linear dependence that we saw. In the previous video we had seen the definition, and in this video we saw a few more questions on how to deal with linear independence and linear dependence. So hopefully now you would have some practice in trying to solve such problems in which one needs to see whether a given set of vectors of a linear vector space are linearly dependent or linearly independent.